In order to proceed now, what I'd like to do is fairly quickly go over how things change if, instead of looking at a Dirichlet-Neumann problem, we were to look at another type of boundary value problem that I've sometimes spoken of for this problem, for this case, right? Let's look at the Dirichlet-Dirichlet problem, okay, and fairly quickly set that up. All right, so now what we're going to do is consider the Dirichlet problem. Okay. And we distinguish this from our Dirichlet-Neumann problem by noting that when I say it's just a Dirichlet problem without any mention of Neumann, what I mean is that all the boundary conditions are Dirichlet boundary conditions. Okay, so what we would be attempting to do for this sort of problem is the following. We would say find UH belonging to SH subset of S, where SH consists of all UH belonging to H1 functions on omega, such that UH at 0 equals U0, as we've been saying. And let's suppose that UH at L equals U sub L. Okay, so we have Dirichlet boundary conditions at both ends. We do not have a Neumann boundary condition at the right end, right? There are no Neumann conditions in this problem. Okay, right. Find UH of this sort such that for all WH belonging to VH, for all WH belonging to VH subset of V, where VH equals the collection of weighting functions belonging to H1 on omega, such that WH at 0 equals 0 and WH at L also equals 0. Okay? All right, find UH belonging to SH such that for WH of this form, right, where you note that SH and VH are different looking spaces because they have Dirichlet boundary conditions at both ends, right? Okay, what do we want to solve here? Okay, what has to hold is the following. Integral over omega E WH comma X sigma H A dx equals integral over omega, I've been saying integral over omega E. It's actually integral over the entire domain omega. Integral over omega WH F A dx plus nothing, right? Because we don't have a Neumann condition. That's it. Okay? That is our weak form. Now, because of the nature of our weighting functions, okay, here's what we have. If this is our domain, omega, okay, and let's suppose that we are working with quadratic basis functions, so those are our nodes for element 1, and those are our nodes for element NEL, right? So this is element omega 1, that is element omega NEL. Okay, right? We know that the sort of basis functions we'll be considering inside here are that and that on element omega 1. Here we will have that basis function for the mid-side node and that basis function, right, for the first node of that element. Observe that in both cases for element omega 1, there is no use of our basis function from the very first node, right, from node A equals 1, global node A equals 1. That node does not contribute a basis function to our weighting function. Likewise, for the weighting function here, our node A equals 2NEL plus 1 has no contribution, right? Okay. However, node A equals 1 and node 2NEL plus 1 do have contributions for UH. It's only for WH that they don't have contributions. Okay? All right. When we work things through, here's what we will get. The matrix vector weak form for this problem. Okay? Global. Here it is. We'll get here C2, C3, everything carries on until we come to the last element. We get C2NEL minus 1, C2NEL. Okay, that's it. We don't get C2NEL plus 1 because we're simply not using that basis function there. Okay? Here we pick up 2E. We are now coming up to what will eventually give rise to our stiffness matrix, right? So here we have 2EA over H. Right? We have our matrix here. Okay. This matrix is going to have contributions when we add up all the contributions coming from the different elements and accounting for the common degrees of freedom across elements, right? We are going to have a contribution that takes on the following form. It will have a form 8 over 3 minus 4 over 3 minus 4 over 3 7 over 3 minus 4 over 3 1 over 6 minus 4 over 3 8 over 3 minus 4 over 3 1 over 6 minus 4 over 3 7 over 3 and so on. Of course, here we know that we get some more terms, right, and so on, right, except that when we come all the way down here, for the last element we get 7 over 3 minus 4 over 3 1 over 6, okay, and here we get minus 4 over 3 8 over 3, okay, and 1 over 6. Sorry, not 1 over 6, it's minus 4 over 3. Right? We get this. That's the last row we get. Okay, in particular, what I want to point out is that if you compare this with the corresponding matrix at this stage for the Dirichlet-Neumann problem, there is an extra row for the Dirichlet-Neumann problem which is missing here. Okay, this would now multiply the following matrix, right? It would multiply D1, D2, so on, all the way down to D2NEL plus 1. Okay, actually I realized that I do need another column here. Sorry, let me just put it in here. I do need another column here, which is minus 4 over 3, 1 over 6, right? That's what I need. Okay. All right. We have this equal to, on the right-hand side, we have our C2, C3 vector going all the way now to C, 2NEL, C, 2NEL, sorry, C2NEL minus 1 and C2NEL. Okay? This multiplying, right, a vector here which is filled with our, which is first of all multiplied by F, A, H over 2. Okay? And here we have 4 over 3, 2 over 3, 4 over 3, so on until the last entry here is 1/3. Right? Actually, no, we don't get the 1/3 entry here because we have only up to C2NEL degrees of freedom, the C vector. Right? As a result, the last entry here would also be 4 over 3. Okay? 4 over 3 would be the entry from the mid-side node of the last element. Okay? The contribution from the last node of the last element, which is the one that I've marked out here, is missing also in the vector that arises from the forcing function. Okay? We have here also then the contribution from traction. Well, we don't have a contribution from traction because there is no traction in this problem. Right? That's it then. Okay? This, actually I don't even need this parenthesis. Okay? That's it. That's what our right-hand side looks like. Okay? Let me point out something about dimensions. This matrix is, this vector is 2NEL minus 1. This vector, as before, is 2NEL plus 1. This vector is 2NEL minus 1, just like the C vector on the left-hand side, because it is the same. The forcing vector now arises only from the uniformly from the distributed forcing, which we are assuming to be uniformly distributed and therefore has a constant f. Okay, so this is also 2NEL minus 1 in dimension. Okay, this matrix that will eventually give rise to our stiffness matrix, we know has therefore dimensions 2NEL minus 1 times 2NEL plus 1. In the D vector here, D1 is known, it is U0, right? It is this Dirichlet condition. This is also known, it is U sub L, that known Dirichlet condition. We will do what we did in the case of the Dirichlet-Neumann problem. We will note that the D1 degree of freedom multiplies out that column. Whereas the D2NEL plus 1 degree of freedom multiplies out that column. Since D1 and D2NEL plus 1 are known, because U0 and UL are given to us, we are going to move those two columns that I've marked over to the right-hand side, just as we did in the case of the Dirichlet-Neumann problem, except that in the Dirichlet-Neumann problem, we did that only to this column. All right? Okay, let's go ahead and do this now. Right? When we do this, we get C2, C3 up to C2NEL minus 1, C2NEL multiplying 2EA over H times this matrix now, which is 8 over 3 minus 4 over 3 minus 4 over 3, 7 over 3 minus 4 over 3, 1 over 6 minus 4 over 3, 8 over 3 minus 4 over 3 1 over 6 minus 4 over 3, 7 over 3, and so on. Now we come down here and it ends in 7 over 3 minus 4 over 3 in the last element, minus 4 over 3, 8 over 3. Okay. All right. Multiplying. In the D vector, we don't have D2 because, sorry, we don't have D1 because we moved it to the right-hand side. We come all the way down and we end here at D2NEL. Okay? Equal to here C2, C3 up to C2NEL. Okay? Multiplying. FAH over 2. The vector here from the distributed forcing is 4/3, 2/3, all the way down until it ends in 4 over 3 at the mid-side node of the last element. The last two contributions are 2EA over H times D1, right, multiplying the first column, right, of our matrix on the previous slide, which is minus 4/3, 1/6, 0, right, zeros all the way down, and minus 2EA over H D2NEL plus 1 multiplying 0, 0, zeros all the way down except till we come to the last two entries, right? And here we get 1/6 and minus 4 over 3. Okay, we close parentheses here. And note that D1 is known because from our Dirichlet condition that is U0, and D2NEL plus 1 is known because from our Dirichlet condition that is UL. Okay, we have here C transpose, that matrix is K, this vector is D. Okay, C transpose has dimensions 2NEL minus 1. D also has dimensions 2NEL minus 1. K therefore is 2NEL minus 1 square. It is a square matrix. C again is 2NEL minus 1. The entire vector here has dimensions 2NEL minus 1. Okay, this is our F vector. Everything sitting inside these parentheses is our F vector. This, of course, is C transpose. Okay, putting it all together, again, for this Dirichlet-Dirichlet problem, we end up with C transpose KD equals C transpose F. Just as we did for the Dirichlet-Neumann problem. Okay? So, for the Dirichlet problem also, we have this. Okay? So, whether we have the Dirichlet-Neumann problem or the Dirichlet problem, we see that C transpose KD minus F equals 0. Now, remember that when we write out our weak form, right, such as in this case, at the top of this slide, I've written out our weak form fairly briefly, and I made a statement on how it has to hold for all WH belonging to the space VH. My question is, when we come down to this final version of the weak form, whether for the Dirichlet problem or the Dirichlet-Neumann problem, where can we see a term that represents the weak form? Right, it is C transpose, right, or the C vector, because that contains the degrees of freedom which are going to be interpolated to form the actual weighting function field, right? They'll be interpolated using the basis functions. So, if our weak form has to hold for all WH, what can we say about this final equation with regard to C? Right, we can say that this equation must hold for all C belonging to R 2NEL. This would be for the Dirichlet-Neumann problem. Or for all C belonging to R 2NEL minus 1, this would be for the Dirichlet problem. Right? Well, if that is the case, one can show from standard arguments that this implies, therefore, that KD minus F has to be equal to 0. Okay? Or KD equals F is our standard form of the finite element equations for linear problems. Okay? And as we saw before, as we did for the case of the linear problem, we say from here D is now equal to K inverse F. How we actually solve this is a different matter, which we won't get into in this series of lectures, but nevertheless, this is the definition of our nodal solution. Right? Once we have that, we can go back and regain our fields by using the basis functions. All right, this is a great place to end this segment.